Next we move into Chapter 16 to study rigid bodies further. The slides, as usual, are linked quite nicely so that you can open them up and click on any particular area of the slides that you wish, so they are indexed nicely. In kinetics, there's many reasons for studying kinetics, but here's two examples. For prosthetic legs, for example, it's important that initial design rely on kinetics so that the device can be safe. If you think about a robotic arm moving an item in space, kinetics are important there because we're interested in forces and how they affect bodies. So in this chapter and in the subsequent chapters, we're concerned with kinetics. So we're really interested in not just how motion progresses and studying the motion itself, which was the previous chapter, but now we're interested in what causes that motion, what changes the motion. So we're going to restrict ourselves to items that are, instead of just being points as we've done so far, we're going to restrict ourselves to bodies, but bodies that are in a two-dimensional plane. And if we have a rigid body, we're going to assume that that body out of the plane is symmetrical on either side of the plane that we're studying. The approach we'll take is to essentially assume that our rigid bodies act like a collection of a large number of particles, and so then we can apply previous chapter knowledge to these problems. In particular, we use the sum of the forces equals mass times acceleration, and we will also apply another equation that we may not have touched on very deeply yet, and that is that the sum of the moments on a body equals the rate of change of angular momentum of that body. Let's focus on this equation for a moment. The left-hand side says the sum of the moments on the body equals, and on the right-hand side you see h sub g with an arrow above it. The arrow indicates that we're talking about a vector quantity. The subscript g indicates that we are taking this moment about the center of gravity for the body, and you see the dot at the very top. So that's the time rate of change of the angular momentum. Capital H is frequently used for angular momentum, and that's what this means. So if we think of a rigid body that's acted on by several forces, so you see the potato body, the idea is that we just have some not very well defined shape of body, and we've got, say, four forces acting on it, F1 through F4. Well, what's going to happen is that the forces are going to cause that body to change its motion if they are imbalanced. And so we're going to assume that the body is made of a large number of particles, and so the motion of the center of mass, the center of gravity of the body, with respect to the reference frame, will just be described from sum of forces equals mass times acceleration. So this is not a different equation. All we're really doing is applying an equation we learned before that applied to particles. We're applying it to a body of size. But if we consider what happens to this body and how it accelerates, understand we're talking about the acceleration of the center of mass of the body. Now, because the body has size, it can also rotate. So we also have to sum moments about the center of gravity. And what we're finding here is that all of these forces on the left-hand side, these four forces, act on the body to produce an acceleration of the center of gravity. That's the dynamic resultant force that you see there, ma bar, and also a rotation, or not a rotation, but a change in angular momentum. Now, one thing that may confuse you about these slides is the direction of that momentum, that changing momentum vector. Let me explain it. It is not necessarily in the same direction as the black arrow above, Ri prime. Okay? This arrow is just in whatever resultant direction is required to represent the effect, the spinning effect, if you will, or the change in angular momentum due to the action of those four forces. So we say that the two are equivalent to another, or equipollent, I believe is the correct term, because the net effect of those four forces is an acceleration of the center of mass of the body and a change in angular momentum about the center of mass of the body as well. Yeah, there's the word I was looking for, equipollent. So basically what this says is the four forces on the left cause the body to accelerate linearly and change its angular momentum. Now, if you think about a rigid slab just in plane motion, not in 3 dimensions, but just in 2-dimensional motion, we've got a coordinate reference frame there, xy, and an xy prime, or x prime y prime coordinate as well. Now, notice that we put the x prime y prime centered on the center of gravity of the body, and for every single point in the body, we can look at the momentum of that point, and if we multiply that momentum, or really take the cross product of the position vector from the center of gravity to that point with the linear momentum of that point, and we do that for all the points in the body and add them all up, we will get the total angular momentum of the body. And so what you see here is the angular momentum. Notice it's not h sub g dot anymore. We're just talking about the angular momentum itself, and we can express it in terms of something called I omega. So you see that at the very end where we have I. I is actually called the mass moment of inertia. And so this is going to be a property of the body, and it depends on how all these points that represent different little pieces of mass in the body are laid out. That's what this is going to depend on. Now, if we differentiate this equation, then we could find that the rate of change of the angular momentum of the body about its center of gravity is equal to I times the rate of change of the angular speed of the body, which is equal to the mass moment of inertia times the angular acceleration of the body. Now, one thing to note here, this parameter I, we've differentiated I times omega dot, right? Or, well, I times omega is what we've differentiated. Notice that the I doesn't have a term to itself. It's constant. And that's because all it really does is it captures how the mass is distributed about the center of mass of the body. That's all that that term I really does. And so it just depends on the geometry of the body. So these results that we've got here are also valid for a body that's not just a 2-dimensional body in the plane, but that has some height, as long as it's symmetrical on either side of this XY reference plane. Now, if the bodies are not symmetrical about that plane, or if we're talking about 3-dimensional motion, then these results are no longer valid. But we're going to restrict ourselves to 2-dimensional motion. So what do we have so far? Well, we've got 2 equations from the sum of forces, right? Sum of forces in the x direction equals mass times acceleration of the center of mass in the x direction. Same thing in the y direction. And now we have an expression for the sum of the moments about the center of mass. And that's just I alpha, the mass moment of inertia of the body times the angular acceleration of the body. Now, one thing you got to be careful about, notice we've dropped the subscript g. Before we had the angular momentum rate of change with the subscript g. Now we don't. Well, that's because this I is being taken with respect to the center of mass of the body. So that's where the g went, and we just don't write it. Because if we just write I, and it's not clear that we're talking about the mass moment of inertia about some other point besides the center of gravity, then you would always assume that it's just the mass moment of inertia about the center of gravity, which is what we need primarily in this chapter anyway. There will be cases when we need something a little different, but we'll explore those a little later. So now we have 3 equations in the plane. So this mass times acceleration, this dynamic force, if you will, is the same result on the body as the 4 forces together, except if those 4 forces are not aligned, if they tend to produce a force couple, then that's going to change the angular speed of the body, and that's what the last equation takes into account. The sum of moments about the center of gravity equals I alpha. So basically, D'Alembert's principle is really just that the external forces, F1 through F4, can be summed up into a dynamic force, essentially the mass times acceleration on the other side of the equation, and it's either an effective force or you could call it a dynamic force. Now, if we have a situation where all of those 4 forces, look at the center row here, all 4 forces on our potato body, if they pass through the same point, then notice that there would be no force couple. So there'd be no change in the angular speed of the body, and we could represent these forces by an equivalent dynamic force, ma bar, right? Remember, acceleration is a vector, just like the forces are vectors. So in this case, the sum of the moments about the center of gravity are simply 0. It's also possible, though, that all of the forces could balance in the x and y direction and yet not pass through the same point, and so there would be a net torque on the body, which would cause a net angular acceleration, and that's the last row here. The most general case is where the forces cause both a dynamic or have a resultant dynamic force and a change in the angular momentum or an angular acceleration. Okay, now some important things or axioms of the mechanics of these rigid bodies. Notice we've got two different forces in the sense that they're placed at two different points on this body. So these two forces, F and F prime, act at different points on the rigid body, but they have the same magnitude, direction, and line of action. And so these forces produce the same moment about any point on the body, and so they are equipollent to each other. So the idea here is that these forces are transmittable. You don't have to worry about that too much. It was built into what we were doing already. That's just something to be complete. Okay, so what we really care about is how the sum of the forces cause angular acceleration and linear acceleration. Now, it's very important that we draw free body diagrams and that we also draw kinetic diagrams. You'll notice that the lower body, what we've done is we've said on the left-hand side, sum of forces equals, and on the right-hand side, let me back up, we're at the upper figure. On the left-hand side, sum of forces equals, and on the right-hand side, mass times acceleration. So this is just Newton's law, right? In the lower figure, what we've done is we've said, let's move that mass times acceleration to the other side, and now notice that the items in blue, the angular acceleration and the linear acceleration, both of those items in blue are the items from the right-hand side of the equation. So we can pretend like this is statics and say the sum of all the forces plus the dynamic forces basically equals 0. So you'll notice that negative I alpha that's in a dotted angled red arrow and the dotted red negative mass times acceleration, those are just reversed in direction and applied to the body as if they were actual forces acting on the body. So what we'll do is apply what we're calling dynamic equilibrium. So we're basically treating this as if this is statics, and this is known as D'Alembert's principle, where you've moved the acceleration terms, the way the body responds, to the other side of the equation, to the left-hand side, where we're summing forces and moments of those forces, and even torques possibly. All right, so basically what we will do is draw free body diagrams as we've done so far and include the kinetic diagram in it so that we can solve these problems. Now notice a lot of times the resulting accelerations are unknowns. In that case, you always assume that they act in the positive direction, because understand that on the right-hand side, when we're saying sum of forces equals, and on the right-hand side mass times acceleration, that mass times acceleration, just from the nature of the equation, assumes a positive direction. And so when we move it to the other side of the equation, we have to subtract it off. So you need to draw it in the positive coordinate directions. So again, we'll have free body diagrams, and we'll also have kinetic diagrams. So if you look at this figure, we've just got a simple cylinder with some type of flexible, maybe rope or something wrapped around it. If we were to make a free body diagram of this system, there's going to be tension in the rope, so you see that on the right-hand side, and there's going to be weight acting through the center of the body. Okay, so you see our regular XY coordinate system with a positive Z direction coming out of the page. You can draw that as an angled arrow if you want to. So we'll isolate the body of interest. That's our first step to solving these problems. So draw a free body diagram. Draw the coordinate system so we know which way is up or which way is positive. Apply all of the forces, so weight, tension, all of these things. and then replace all the supports with forces. Okay? Finally, draw any dimensions, angles, distances, anything like that that we need, and then put on the inertial terms. So on the left-hand side of this equation, we have sum of forces, and on the right-hand side, we have the resulting angular and linear accelerations. So to draw the kinetic diagram, we'll isolate the body of interest, the free body, it's the same as it was before, and then draw the mass times acceleration of the center of mass of that body. So we end up with three equations technically, because we've got two sum of forces, an x and a y, plus a sum of moments equation coming out of the page. All right, so let's do that for this body. We need to draw the free body diagram and the kinetic diagram. We know that the bar has a mass m, and we know that there's a force P applied at the bottom of the bar. So let's see if we can do this. So the first step is to isolate the body. Okay, well, there's the body. It's isolated. Now what? Well, draw some axes. Okay, there's our coordinate axes. We've defined which way is up or which way is positive. Draw the applied forces. Well, there's an applied force P. There's also an applied force, which is the weight, right? Replace supports with forces. So notice there's a support at C. Now, of course, at C, there's no moment. There's only forces. We're assuming frictionless pin at C. Label any dimensions. So there we go. And then draw the kinetic diagram. So we've got our free body diagram, and now we need a kinetic diagram. Well, that's easy. All we have to do is draw the body again and put on the kinetic forces. So we've got a mass times acceleration in the y, mass times acceleration in the x, and I alpha. This is the easy one, because all you really have to do is draw the body again, copy the coordinate system you've already made, and call it accelerations, both linear and angular. So it's very simple. Okay, here's another one. Here's a problem we'd like to work through. A drum of 4-inch radius is attached to a disc of 8-inch radius. The combined drum and disc has a combined mass of 10 pounds. A cord is attached as shown, and a force of magnitude P equals 5 pounds is applied. The coefficients of static and kinetic friction between the wheel and ground are 0.25 for static and 0.2 for kinetic. Draw the free body diagram and kinetic diagram for the wheel. Okay. So first, isolate the body. There we go. Draw the axes. There we go. Apply forces, weight and the pulling force P. Replace supports with forces. Well, the only place there's support is in the contact between the ground and the wheel. So there we go. Now we have to be careful here. There is friction, so there's a normal force and there's a frictional force. But notice, please don't make the mistake anymore of thinking that the normal force is equal to the weight force. That's not the case. We're in dynamics now. And so what's happening is as the body accelerates, the normal force could be all sorts of things. Okay, so we'll just please try to break that in your mind of saying, well, the normal force is just equal to the weight force. That's not the case. Next is to add dimensions. So here are some relevant dimensions, and then draw the kinetic diagram, which is as easy as drawing the body again and copying the coordinate system, labeling those coordinates with, rather than x, y, and a z, label them with the dynamic forces in the x, y directions and in the angular direction, or the z direction. What about this one? The ladder AB slides down the wall as shown. The wall and floor are both rough, indicating that there's friction. Draw the free body diagram and kinetic diagram for the body. Okay. So first of all, isolate the body. There we are. Draw the axes. There we go. We know which way's up. Apply forces. Well, there's weight. What else is there? Well, there also are support forces, right, from the wall. So these support forces are going to be normal forces in A and in B, and there will be friction as a result. Now, how do you know which way to draw the friction forces? Well, notice that they told us that A is moving to the left. If that's the case, then friction always acts opposite of motion. And so the frictional force at A is acting to the right, and obviously point B is sliding down the wall, therefore the friction force at B is acting up. Finally, add dimensions. Well, there we go. There's some relevant dimensions. And then draw the kinetic diagram. So copy the body, put the axes on top of it. Okay, how about this one? This is a sample problem, and I don't actually want to go through the sample problems, at least not most of these, so let me skip it. I want you to go through them. I have my own sample problems, but I'd like you to work through the van and there's another one afterwards. There's a thin plate being held in place. I'd like you to pause the video at this point if you're watching it and go through these. Now, along the way, there is one example, I believe it's this one. I want to not necessarily work through all of this. As I said, I'll have my own example problems. I do want to point out something to you, though, because the chapter in your book does not do a good job, in my opinion, of talking about the term I, the mass moment of inertia. And I want to make sure that that is clear to you. They've given us a radius of gyration of 8 inches. Now, that radius of gyration is actually closely related to the mass moment of inertia. I don't normally ask you to read the book, but you really need to at this point. It's only about 5-6 pages. It starts on page 894, and it's in the appendix. So open your book and go to that page now, if you would please, and look at the bottom of page 894, equation 9.29. It says that I equals k squared m, where m is the mass of the body and k is the radius of gyration. So what they've given here, when they've told us radius of gyration is 8 inches, they've given us k. So if we know the mass, which we do, the 12 pounds mass, then we can calculate the mass moment of inertia. But you have to be careful about the units, because the mass moment of inertia involves mass, not weight. So notice that they've got the equation I mentioned, I equals mk squared, but mass is weight divided by the acceleration of gravity. So they've written in 12 pounds force divided by the acceleration of gravity, 32.2 feet per second squared, times k squared, where k is 8/12 of a foot, and it's squared. That's the radius of gyration. Now be careful here. Some of you are probably used to using an ijk coordinate system, and you look at that k with a bar over it and you think that it's the unit vector in the z direction. That's not the case. This is simply the radius of gyration squared. So that's all I really wanted to point out, and I'll let you go through the rest of that example on your own. So after you've gone through all of those example problems in the slides, let's approach this concept question. The thin pipe P and the uniform cylinder C have the same outside radius and the same mass. If they are both released from rest, which of the following statements is true? A, the pipe P will have a greater acceleration. B, the cylinder C will have a greater acceleration, the one on the right. Or C, the cylinder pipe will have the same acceleration. Well, really the question centers around the mass moment of inertia. Now, as I said, you need to go into the appendix in your book and read from page 894, let's see, all the way through page 899. Now, 899 is a page that deserves a tab in your book because it is a page you will want to reference where it'll tell you how to calculate the mass moment of inertia I for many common shapes. If you've ever seen a person walk a tightrope with a long stick, the reason they do that is because that stick has not necessarily a lot of mass, but it has mass far out from the center of rotation. And so if the person needs to right themselves, they can actually push on the stick to do it, and the stick won't move much because the stick has a fairly high mass moment of inertia. There's a lot of mass far out from the center of rotation. Well, this page, page 899, tells you how to calculate the mass moment of inertia of several different shapes. And so what you'll notice is that it has, let's see, in particular interest for us is a thin disk. And there are two different possible inertia moments, one about an axis running through the diameter and the other about an axis going through the central axis of rotation of the disk. Now, the one we're interested in, the mass moment of inertia we're interested in, is the one that represents the motion of the wheel. In this case, it's rotating about its axis. So that would be Ix, and it's equal to 1/2 mr squared. So if you know the mass of the disk and you know the radius, well then the moment of inertia is 1/2 mr squared. Okay, but how does that help us here? Because neither, well, the one on the right is a simple disk. It's a cylinder, essentially. The one on the left, though, looks like a cylinder where a cylinder has been subtracted from it. Now notice that both of these have the same amount of mass. And it turns out you can actually take the difference between the solid cylinder and the cylinder that would be there in the center. But what you would find is that since the cylinder on the left has as much mass as the cylinder on the right. The thin pipe on the left has the same amount of mass. The fact that that mass is distributed far away from the center means that it will have the higher moment of inertia. That means it'll be harder to get it to start spinning. And so what will happen is cylinder C will have a greater acceleration. It will be easier to get it to start rotating. Imagine trying to get a flywheel to rotate. Okay, so as an example of flywheel, you can think about a bicycle wheel. If you've ever turned your bicycle upside down and started to pedal, there's two things going on. First of all, you feel a lot of resistance. And part of the reason you feel resistance is because there is an increased gear ratio. In other words, the wheel turns faster than the pedals do. But all that's really doing is amplifying the inertia of the bicycle wheel itself. And so you actually feel it. And so that inertia is in the wheel because most of the mass is far from the center of rotation of the wheel. So the answer to this is that the cylinder will have the greater acceleration. The next thing we're going to approach is constrained plane motion. So far the bodies have been free, but now they're going to be constrained to other bodies. There may have been supporting forces, but no other bodies attached. So now we're going to study what happens when you have bodies attached to other bodies. All right, so in this case, you see a mechanism. It's got a bar, ground, and two sliders. And most engineering systems are like this, where they move with constrained motion. Now, if we try to analyze this, it's going to take a few more techniques than what we've developed so far. So the constrained motion at this point, if you try to draw a free body diagram of, say, just the connecting bar between the two, we could do what we've done so far, draw the free body diagram, the kinetic diagram, and for this mechanism it would probably work out okay because, let's see, we just have a normal force at B, we'd have a normal force at A, there's a force P pulling on it and a weight W. But what if the two blocks had mass? Well, then they would have to be accelerated as well, right? And so that would be a constrained motion where it's constrained to other bodies. So we have to start off with a kinematic analysis and solve for the forces and the accelerations and so on. In fact, a general principle of this chapter and of this body motion in general, or pretty much any motion, is you have to solve for, first of all, position, and then velocity, and then acceleration. And get as many equations as you can from the kinematics analysis, and then add the kinetics on top of it to find any forces or torques or anything like that. What if we have non-centroidal rotation? What do we do then? Well, in that case, the body rotates, but it doesn't rotate about its center of mass. And so then we have to consider the center of mass as if it's moving along a path, and of course that would be a circular path about whatever point the body is constrained to rotate about. So we can consider the center of mass, or all the mass of the body, at least for the sake of the linear acceleration, we can consider it all being concentrated down to the center of gravity of the body. And this is a really powerful technique because we're just basically employing all the tools that we had when we were studying points, bodies as points, and how they move. So point G is going to move on a circular path, and therefore it will have a tangential and normal acceleration, which we know how to deal with. Obviously, we have the kinematic relationships between the motion of G and the motion about O. I think that's a misprint. Yeah, kinematic relation between the motion of the mass center of G and the motion of the body about it should be about O, not about G. I'll fix that. By the time you get the slides, that should be fixed. But anyway, the tangential acceleration magnitude is simply equal to the vector r, which goes from O to G, times the angular acceleration of the body, while the normal acceleration is equal to r times the angular speed of the body squared. And we've discovered that before. So what we're going to do is use kinematic relationships to eliminate the tangential and normal acceleration from the equations that we write in order to pretend that these things are in dynamic equilibrium. Okay, so if we've got a balanced disk, so it's not flopping over, it's just rolling perhaps, and it's rolling without sliding, sometimes it's beneficial to consider the motion all the way to the acceleration. So if you think about the center position of the disk, you can call it x, right? So wherever you attach a coordinate system to ground, the position of the center of mass of the disk is x, and that will the position of the center of mass will advance based on how much the disk rotates. So it'll advance based on r theta, right? Because think about it, if the disk rolls one complete turn, then it will have moved in the direction x by an amount equal to the perimeter of the disk, right? Which would simply be pi d. And that's what we would get, right? Because it would be 2 pi radians, that'd be the theta piece, times the radius, and effectively that gives us pi times d. So differentiating that equation twice, you end up with the acceleration equals r alpha. Now, if the disk is rolling without sliding, then that means that the friction force that's being applied is less than the friction coefficient times the normal force between whatever surface this is and the bottom of the disk. And in that case, there is a relationship between the acceleration, or the linear acceleration, and the angular acceleration of the disk. If we're at the point, if we're at the limit of what friction can do, and the friction force is equal to the static coefficient times n and not just less than that, then the linear acceleration and the angular acceleration are still related to one another. But if there is rotation of the disk and the disk is sliding, if it's slipping, then the friction force is equal to the kinetic friction coefficient times the normal force, and the angular acceleration and linear acceleration of the center of mass of the body are independent of one another. Now, think about a disk that has that's designed so that it's unbalanced, right? So its center of mass is at G, but it's rotating not exactly about O. Technically, it's rotating about C, but you can think of it as rotating about O. Well, the acceleration of the center of gravity, if you know the acceleration of the center of the disk of O, well, then the acceleration of the center of gravity can be written as a relative acceleration equation. The acceleration of point G is equal to the acceleration of point O plus a relative acceleration vector between G and O. And so what this does for us is it allows us to use what we were doing, I believe, in chapter 15, where we were writing the relative acceleration in tangent and normal components. So here's a sample problem. I do want you to go through this. There's a couple of things to note that I don't think they state very well. One is that the bar that's labeled BO, that bar is connected through a shaft to the gear, which I would say is labeled A. So just know that, and I believe there was another thing I wanted to mention in this. Let me see if I can find it quickly. I think there was a trick along the way. Oh yes, since that bar and gear E are attached to one another, their angular accelerations are equal. Now you might be confused about why they do some of the things they do in this problem. You'll notice that they've got, on the left-hand side, they've got the free body diagram with all of the reactionary forces, the externally applied forces. So it's kind of weird because it's like they're taking the bar and the gear and they are pretending they're together and also analyzing them as if they're separate. So if you think about this, you'd realize that there are actually torques between the bar and the gear. And so I'm not real fond of this example problem because they didn't really make it two separate bodies. But then they try to analyze it as if it's two separate bodies with the moment of inertia, IE and IOB. And so it gets a little bit confusing along the way. IE, what they do there, IE alpha, to get that dynamic moment, what they're doing there is just considering the gear as a disk. And then they write a relationship between the, well here, let me move ahead so I can describe it all at once. That'll be easiest. I think there's, yeah, one more equation. Okay, so then they're writing a similar equation for the dynamic forces, right? So you've got MOB times the acceleration in the tangential direction. Now look at this and think about it. What they're doing is they're writing the dynamic force that's applied to the center of gravity of the bar and writing it in terms of a tangential and normal component, okay? And so that's what the next two equations are. And then finally, they write IOB alpha. That's the part I wanted to get to because it's confusing why these two bodies are together and yet they seem to be separate in their I alpha terms. Well, there is a way to approach this that would put those two together, but you have to understand the parallel axis theorem. Now, if you have had strength of materials with me, we actually have used the parallel axis theorem when we were talking about the second moment of area. And if you look in your book on, let's see, page 898, equation 941, I believe is the one I want. Yeah, that's an example of the use of the parallel axis theorem, but the parallel axis theorem itself is stated on page, here we go, 896, equation number 933. So in this equation, what they're doing is they're calculating the mass moment of inertia of a body about some other point than the center of gravity. So they write that that moment of inertia equals, and then they've got I bar. Well, that I bar is the mass moment of inertia of the body about its center of gravity, but then there's a correction term because we don't want the mass moment of inertia about the center of gravity. They've got this correction term md squared. Now m is the mass of the body and d is the distance between the center of gravity and the particular point where we want the mass moment of inertia, the I on the left-hand side of that equation. And I wanted to make sure that was clear. This example is a little bit difficult to wrap your head around because of them separating out two mass moments of inertia so they can calculate them easily based on the geometry and yet putting them together as one body. Now understand that they are one body and so their angular accelerations are the same. But what they've got here, these I alpha terms, are about the center of gravity and they'll be able to simply add them together. That's effectively what will happen. So they've copied it from the previous slide and yeah, there we go. So you see in this sum of moments equation, they've taken all of the forces that cause a moment. Well, what forces are there? The weight of B acts through the center of rotation, so that doesn't cause a moment. The reactions act through the center. The weight of the gear acts through the center. So none of that is important. The only thing that causes a moment is the force F from the mating teeth. And so you notice that they've got F times the moment arm on the left-hand side. That's the sum of all the moments acting on these two bodies about O. And then they've got I alpha for both the gear, I guess they're calling that body E, and IOB, the bar, okay? But then they've got this other term in there that's kind of weird. You may wonder where it comes from, this MOB, tangential acceleration, times the moment arm. What is this? And why don't they have the normal piece? Well, think of MA as a dynamic force. So MOB, A in the normal direction acts through the center, right? But the other force that is attached to the center of mass of the bar acts with a moment arm about O. And that's why it's included. So it's kind of a backwards way of going about this, but I wanted you to understand where all of these terms come from. So then they finally finish solving all the equations and get the right answer. Okay. Now, this problem is particularly interesting to you because it's applicable to the marble roller coaster. This problem analyzes a sphere and says, okay, what would the acceleration of the sphere be if it were simply sliding down the incline with no friction versus rolling down the incline where we have to not only increase its linear speed, right? So linearly accelerate it, but we also have to angularly accelerate it. Because now it's going to have inertia and it's going to resist rolling, just like the mass resists acceleration. So what we're going to do is go through the regular solution process for this. I want you to go through this in detail. I'm going to click through it quickly because again I have my own examples that I'll record for you. But I want to come to the end and point out something. You'll notice, I think that may have been one of them. Yeah, here we go. So they've included the friction force here, and this result, the acceleration equals 11.5 feet per second squared. That's the acceleration of the center of mass of that body if it has to also rotate, if it has to also angularly accelerate, not just linearly accelerate. So then they go through and they calculate the angular acceleration itself and back calculate the friction coefficient. Okay, fine. Now, after that, they play with kinematics and say, okay, what's the velocity after 10 feet of acceleration? What if then, but the next question is, what if there is no friction? Then what happens? Well, then the equations are a little simpler because there is no I alpha, okay? There's no angular acceleration. In that case, the linear velocity comes out to 17.94 feet per second versus 15.17 after 10 feet. And so the effective acceleration is higher now, right? We've got 16.1 feet per second squared, whereas when we had to take into account the angular acceleration of, you can think of it as the marble in your example or in your project, in that case, the linear acceleration of the center of the marble was only 11.5 feet per second squared. So you see that the angular acceleration does make a sizable difference. So I'll let you study that example in detail. I just wanted to point out what was going on there and how useful that is to your project. There are some other examples. I think you can handle these, especially once you understand the moment of inertia I. So I can't stress enough how much you need to make sure and go through that appendix. Let's approach this concept question finally at the end of the slides. What would be true if the floor was smooth and friction was 0? Option A, the bar would rotate about point A. Well, that doesn't make sense, right? Because the center of gravity of the bar is up in the center of this bar. We're assuming it's uniform. And so there's a force coupled between the normal force and the weight force. That's going to make it rotate. That makes sense. But what's going to keep the bar from sliding along the ground? The only thing that could keep it from sliding so that it rotates about A is if there was friction. But there is no friction, so A doesn't make sense. The bar's center of gravity would go straight down. That's one possibility. That would make sense because A would just slide sideways and the center would go straight down. That makes sense. C, the bar would not have any angular acceleration. Oh no, the bar is definitely going to have angular acceleration because think about it. This is a force couple that is an imbalanced torque. And so that imbalanced torque equals I alpha, and so there's going to be some alpha. There's going to be some angular acceleration. And so we, in fact, just from intuition, you know that this bar is going to rotate. If it's released from rest, it's not rotating now, and it starts to rotate, it must have had some angular acceleration. So the answer would be B.